Wow. I mean, to be honest, you've never seen anything like that. So this is a unique experience. I'm going to refer back to that orchestra. Is it orchestra? Look at this guy. This guy's so sad. We are going to do a lot today. We're going to do lessons 3 and 4. We're going to learn how to solve a whole lot of equations. We're going to start on page 655. Our goals today, we're going to solve exponential equations using the change of base formula a little bit, but not too much because we know how to use our calculator to do some things, and we're going to solve exponential equations by taking the log of both sides. Let's get started with a little bit of a review. We're going to review some of this change of base stuff that we have done in the past, right? So, like number 1 here, we're on page 655. By the way, you're going to have to keep it tight here because we're going to be flying. So 2 to the x equals 32. We already know how to solve this from before. We just write it with a common base, right? So what do you get? 2, 4, and then 8, 16, and then 32. So that is what, 5? 5 of these? So then we get an x equals 5. And we know that's true because the bases are the same, so the exponents have to be the same. Then we can start figuring out ones like number 3 here. We have x to the third. That equals, well, I know that 27 is actually 3 to the third. So the exponents are the same. The bases must be the same. We get x equals 3. What do we have here? Well, this is 5 to some power equals 625. Well, 5 times 5 is 25. Times 5 is 125. Times 5, that must be a 4. So 5 to the x, we're going to say, equals 5 to the 4th power. Therefore, we know that x equals 4. And then lastly here, some number to the 7th power equals 128. That's got to be a tiny number because to the 7th power, come on, x is going to equal 2 for that one. So that's all review, right? I mean, that's using a common base to solve these. Easy enough. Now we're going to learn the change of base formula, which honestly is becoming a little bit obsolete. We're on page 658 now. This is becoming obsolete because we have calculators that will do a lot of this math for us. But there was a time when we didn't have calculators that would do a lot of math for us. So I'm going to show you some examples here. Here's the change of base formula. It states that the log base b of c is equal to log base a of c over log base a of b. So let me show you what that means. Here are 3 examples that we have, and they're in different bases, right? And so back in the olden days, like when Sullivan was learning stuff, right, before, the wheel and things like that, we only had tables that told us common bases or common logs, right? So log base 10, the common log. So to figure out a base 8 log, they would actually just rewrite it like this. The log of 40 over the log of 8. And I can go into proving why this is true. It's actually in your textbook. But yeah, we're short on time a little bit, so we're going to kind of run with it. But basically, the way it works is you have the log of 40 over the log of the base, and these are equivalent to each other. So let's pull up a calculator just to check it out real quick. So here is our trusty calculator. I'm going to hit math and then up twice. We already learned how to do this, right? And we get log base 8 of 40. So we're going to figure out approximately the exponent used on 8 to get 40 is about 1.77, right? So now if I just say the log of 40, and I close that off and divide it by the log of 8. Guess what I'm going to get? Shocker, 1.77. So this is a nice little formula they used to use, back in the olden times when Sullivan was learning, to help us figure this out because we had a table that told us all of the common logs. They told us log base 10. So we could just rewrite that as log of 12 over the log of 2. And then they could put that in their calculator and figure it out. This last one would be the log of 120 over the log of 5. Easy enough. Well, that's the change of base formula. So just be familiar with that. If you need to, you can actually use common logs to figure that out. But as I said, like our calculators now, with log base in our calculator, we don't need to worry about that. And it actually makes our life a whole lot easier. So now we're on page 660, and again, this is a lot of review. It's like 2 to the x equals 64. So we have solved this before just by getting a common base, right? 2 to the x equals 2 to what? So we got 2, 4, 8, 16, 32, 64. That's 6, right? So here we're going to get x equals 6. And over here, we need to find some number to the 3rd power. Well, 125 I know is 5 to the 3rd power, right? So if y to the third power equals 5 to the third power, if the exponents are the same, the bases have to be the same. So here, y would equal 5. That is easy enough. Pull a box around that one too. So let's go down to number 2 here. Solve each logarithmic equation. We're not going to explain the strategy right now. We're just going to solve it. Look at this. Common base with a log. Guess what? Common argument. So w here has to equal 20. And what do we have? A common argument. So guess what? The bases have to be the same. It's all about that base. All right, so this is stuff that we kind of know. We've talked about it. We've used it. It's a lot review. So we'll use this knowledge as we go to page 661. We're going to look at Shen's and Danielle's solutions to the exponential equation 4 to the x minus 1 equals 50. That's a little bit different for us, right? Because we have an x minus 1 in the exponent. So let's see how Shen has solved this. We have 4 to the x minus 1. We notice what happened here. It looks like they took log base 4 on the right, which means they did log base 4 on the left, and it brought that exponent down. Okay, so now look what Shen did. We said log base 4 of 50. Shen did log of 50 over log of 4, right? And that is that property I just taught you. And then they did plus 1 to get the 3.822. Well, Danielle did it a little differently. Danielle took logs right at the beginning and then pulled that exponent. This is an exponent, right? So we used that power and brought it down front. And so we have x minus 1 times the log of 4 equals log of 50 divided by the log of 4. This is what Danielle did, by the way. And we get both sides. We're going to get log of 50 over the log of 4 equals x minus 1. You get the same answer that way. So this is the way that we used to have to solve these things because we didn't have log base. We couldn't do like base 8 or base 4 to solve them. Today we're going to learn how to use log base. I mean, that's more efficient. And so we're still on page 661, but I'm going to show you how to solve this using log base because that's really the way we want to do it. And we're going to get a lot of decimal answers. So that's fun, right? All right, so we get 8 to the x power equals 38.96. So the way that we've done this in the past, if we have taken a log with whatever the base is. So this is log base 8. We're going to do that on both sides. We're going to take a log base 8. So that's going to give us log base 8 of 8 to the x is going to equal log base 8 of 38.96. All right, now the benefit in this is log base 8 of 8 to the x. These kind of cancel each other out, and you're left with x is going to equal. And now we have this ugly thing, but you know what? As I said, in the past, we couldn't evaluate a base 8. We didn't have that. But now we have Cal. Where'd Cal go? Get back here, Cal. There it is. So we can actually just put this in our calculator and figure it out. Log base 8 of 38.96. We're going to hit math. We're going to go up to log base. So it's log base 8 of 38.96. Guess what? Figure all that out. We get 1.76. And that'll be our answer for this one. It says round the nearest thousandth. So that would be 1.76. I need one more decimal point here. We got to look at it. Bring it back up. It's a 1. The next one's a 3. So we stay at a 1. Right? And some of you have experienced that rounding problems on the last mastery check. And we're all done there. That's easy enough, right? Because we can use log base. So now we're moving on to page 664. I told you we're flying. We are so flying. And we have these equations here. Now, how can we solve those? Now, the variables here, it's in the exponent above the 2, right? So we have to isolate that first. We're going to get that by itself. So the first thing we can do on number 1 here, we're going to subtract 6 from each side. They would cancel. Here's our balance point in our equation. We're going to get a 24 on this side. We're going to get a 2 to the x minus 5. Now, as we've said in the past, how can we kind of get rid of that or pull that exponent down? We can take a log base 2. Okay, and we're going to do that on both sides. Log base 2. So that's going to give us log base 2 of 2 to the x minus 5 is going to equal log base 2 of 24. So now what? These kind of cancel each other, right? We get x minus 5 equals log base 2 of 24. I can add 5 to each side. We'll add 5 here. But don't think you can just add 5 to that 25. It doesn't work like that. These will cancel. We're going to x equals log base 2 of 25. And then when we're done that, we add 5. Let's bring up the calculator. Notice that the plus 5 is after the 25. We're all done with this. So it's going to figure out the log base 2 of 25, and then it'll add 5 to it. We're going to get 9.64. So that'll be our answer for number 1 there. X equals 9.64. Now look at number 2. Notice how it's a little bit different because we have a coefficient in front here, a 7 times 2, and that's raised to the 3x power. So the first thing we can do is get rid of that 7. We're just going to divide by 7. We're going to do the opposite of multiply, and they will cancel each other just like a regular equation. We get 2 to the 3x equals 840 divided by 7. Cal is going to tell us 120, right? So that's what goes on this side. And so at this point, we can do log base 2, right? Because the base here is 2. So log base 2 on this side, log base 2 on this side. That's a base, got to be careful. So what are we going to get? Log base 2 of 2 to the 3x is going to equal log base 2 of 120. These will cancel each other out. We're left with 3x is equal to log base 2 of 120. Now what? Now we got to divide by 3. It's like a regular equation. It's 3x. We divide by 3. We'll get x equals log base 2 of 120 divided by 3. We can put that right in the calculator and get 2.30 on that one. 2.30. Right? So these are pretty easy because it's just opposite operations. Just like if the x was there, we would isolate the x and then solve it. Easy enough. So I do believe that now is a great time for you to try one. Try number 3 all by yourself. Go ahead and complete number 3 on page 664. Pause the video and try number 3. Okay, so hopefully you got what I got. What do we do first? We add 5, right? Then take log base 4, both sides. And then these things will cancel out. And then we're left with x minus 3. That's the exponent that comes down. We add 3 to each side. And again, be careful. You can't just add 3 to the 21 because it's log base 4 of 21. That's one identity right there. That's a one thing by itself. But you figure that out and then you add 3 to it, which in our calculator looks like this. Log base 4 21, and then we add 3 to it. And we get 5.196. If we go to the nearest hundredth, what are we doing here? It doesn't really say. So we'll go to the nearest hundredth. We've been doing that. 5.20, right? Or maybe 196. We'll tell you what you need to go to. It does change. Generally, the nearest thousandth. I'm going to take that off. We'll go to the nearest thousandth. 5.196. Now we're safe. All right, let's try number 4. We have to, look at this. We have to get that x by itself, right? So there it is. So we got to get rid of the 10. It's 10 times. So we're going to divide by 10, both sides. That's not unreasonable. They will cancel out. So we're left with 3 to the 2x, and it's all over 2. And that will equal, I can do this one in my head, 36. So now I can get rid of that 2 on the bottom, to be honest. I can do times 2, and I can do times 2 on this side. They will cancel. So I'm left with 3 to the 2x is going to equal 72. So now guess what we need to do? You guessed it. The base is 3. We're going to do log base 3. Oh, lost my pen. Log base 3 of 3 to the 2x, because that'll make them cancel out, right? Equals log base 3 of 72. So these will cancel out. I'm left with 2x equals log base 3 of 72. Now what? You guessed it. Divide by 2, both sides. So my final answer is going to be x equals log base 3 of 72. The answer divided by 2. Let's figure that out in the calculator. So I get x equals 1.946 after I plug it in the calculator. Let's make sure that that is also what you get. You got to make sure you actually plug it in and get the right answer. Let's box it to the nearest thousandth. Now, there's one for you to try, but I'm going to give you a little bit of guidance, right? Where is it? Number 5 down here. I'm going to tell you what to do in which order. I need you to pretend like this is 2. The x is up there in the exponent, so think of this term as like the x. So it's like 2x plus 1 equals 55. What would we do first? So the first thing I want you to do is I want you to subtract 1 from each side. Then I want you to divide by 2. And then I think you can start taking logs and you're good to go. Okay, so pause the video and do number 5 all by yourself. Go. Okay, so welcome back. Here we have the resultant after I subtract 1 from each side. 2 times 3 to the 5x equals 54. The next thing that I had told you to do was divide each side by 2. You get 3 to the 5x equals 27. Now here's where I'm going to throw you a curveball. You probably did some logs there, but I'm going to show you that this we can do a different way. Guess what we can do? Common base, right? So I see that that's 3 to the 5x power. This is 3 to the 3rd power. I've learned that by now. So the bases are the same. I can set the exponents the same. It doesn't matter which way you do it. If you did it the other way, you would get the same exact answer of x equals 0.6. Are you serious? You could do either way? Yes, absolutely. Let's show the other solution here, just in case you don't believe me. All right, here we go. We get 3 to the 5x equals 27, and so we take log base 3, right? If we were going to use logs there, we would do that. Of course we would. We get 5x equals log base 3 of 27. We divide by 5. Here's what Cal tells us right here. Log base 3 of 27 divided by 5. Boom, 0.6. That is amazing. We get the same answer. Common base, we're using logs. That's great. All right, let's move on. We're now into lesson 4, and we're going to learn different ways to solve logarithmic equations, but we kind of already learned some. Like, we went through it. That last lesson was just the change of base, which, you know, we kind of don't use that so much. So we're going to start on 667. Whoa, I lied. We're going to go to 672. Let's just go to that and start solving some of these equations, shall we? The more practice we do, the better off we'll be. So we're just going to, I know the directions say circle the equations you can solve more efficiently with one way or the other, but we're just going to start solving some of these. And again, I might do them different ways. There are different ways to do these, and no way is better than the other necessarily. It's whatever you enjoy doing. So let's actually just figure this one out. Like this one, this is log base 4 of x plus 3. One way to get rid of that log is we can raise 4 to this power, because this is the exponent that when I put it on 4, I get x plus 3. So if I put that whole exponent on 4, guess what I'm going to get? X plus 3. What? But if I raise this side as a power on 4, I have to do the same thing over here. So I have to do this would be 4 to the 1/2 power. Now I know that 4 to the 1/2 power, 1/2 power is a square root. So 4 to the 1/2 power actually just equals 2. And we can check that with our calculator. I know some of y'all don't believe me, but 4 to the 1/2 power when we figure it out equals 2, because the 1/2 power means square root. So now we just get this really easy equation here with x plus 3 equals 2. So we can subtract 3 from each side and we get x equals -1. Now, here's where we got to be careful. We got to check that argument can never be negative, right? That's one of the things we learned from the last lesson. But here when we solve it, we get x equals -1, but when I plug it in, it's -1 plus 3. So that ends up being positive, so we're good to go. That is one way to solve this problem right here. Let's just keep solving, and then we'll find different ways to do it. Let's go to B. We have log base 4.5 of 9 equals x minus 1. You know what I would do with this one? Because these are all numbers in here. There's no variables. I can just pull up the calculator and figure that out. Let's do that. Let's just pull up the calculator. I hit math. We'll go up to log base. And then I'm going to just calculate the log base 4.5 of 9. And it's going to tell me a number here that's going to be a little bit ugly, but it's 1.461, we'll say. So this is all equal to 1.461. That is an ugly number, but that equals x minus 1. Well, that's an easy equation. I can just add 1 to each side. So I add 1 here. This is going to give me 2.461 will equal just x, because they will cancel. That is my answer for part B. I tell you what, that's enough for right now. I don't want to make this video too long, so we'll come back in the middle of lesson. It's not really the middle. We started lesson 4. We'll finish lesson 4 in the next video. Good luck to you out there. This is Mr. Kelly in K-Town. Remember, it's nice to be important. It's more important to be nice. See you.